So this is the first problem. Let's read it at first. You can see the picture at the bottom here. We actually need to calculate the optimum fin spacing. We discussed during our lecture and the importance of the spacing and the optimum fin spacing. So definitely we're not going to discuss it right now because it will just increase the length of the video. So here it is wall dimensions given like 12 centimeter wide and 18 centimeter high vertical hot surface, and it is in 30 degrees centigrade air. Is to be cooled by a heat sink with equally spaced fins of rectangular profile. So you can see the drawing here, the rectangular fins and the length, the void, the height. Okay, so the thickness of the fins, you see it is given t equal 1 millimeter or 0.1 centimeter, and it is 18 centimeter long in the vertical directions. So you can see the length is given L equal 0.18 meter and the height is 2.4 centimeter. So from the base, so the length it is given in the vertical directions, and the surface temperature it is given 80 degrees centigrade. So we need to determine the optimum fin spacing. So we need to calculate the fin spacing, like the optimum spacing, and finally we need to calculate the rate of heat transfer. So this is actually the problem. So the two things we need to calculate, the spacing and the rate of heat transfer. If we start with this problem here, so the first thing we need to do is we need to calculate the rate of heat transfer. So okay, maybe let me start with the new one. Yeah, so the rate of heat transfer, we know Q, it is equal H's, a Newton's law of cooling actually. So, and the temperature difference Ts and T infinity. That's the temperature difference. So here what we need to know is the surface area. The surface area, it will be actually, the 2NL H's. Because, we may discuss it later. So we actually need the heat transfer surface area, AS. So N is, this, it is actually 2N. Okay, so N is actually the number of, the fins. When we calculate the surface area, we need the length, we need the height for the both, and we will consider how many number of fins we have here. So here actually, if we want to calculate the number of fins, then it is N equal, we know the formula we discussed during the lecture, it is N equal S plus T. S is actually the spacing. Okay, W is the weight and T is the thickness of the fin. So once we have this, then what actually this sort of information we need for rate of heat transfer. And then the other important thing is we need the optimum spacing. So we will calculate the spacing, the SOPT. It is the formula actually from the literature, it is 2.714 and L over the Rayleigh number in the power 0.5. So to get this, we need the Rayleigh number. So now we will calculate the Rayleigh number, RAL. It is equal, G beta and the temperature difference, characteristics length over the viscosity square and Prandtl number. So this is actually the total, the flowchart of this problem we need to follow if we actually want to get the optimum spacing and the rate of heat transfer. So if I start with the solution now, so maybe as usual what we can do, we can write the assumptions, because the heat sink, it is equally spaced and it is rectangular fins, and we need to calculate the spacing and the heat transfer. So if we write down the assumptions, so here our main assumption is we are not considering the unsteady case, so it is a steady operating conditions. Okay, and air, we will consider it is air is an ideal gas. Okay, air is an ideal gas. The thickness, it is, if you see from the figure, the thickness, it is very small compared to the spacing, so we cannot neglect the optimum fin spacing, so it is applicable here. So that's our third assumptions. I'm not writing here. So thickness is smaller than the spacing. Okay, so thickness it is smaller, relatively smaller than spacing. So that means the optimum fin spacing, it is applicable. It is applicable. That we need to calculate, and we will consider the fin surface temperature. It is isothermal. Okay, fins are isothermal condition. Fins are isothermal condition. That means the base temperature. So I'm not writing everything here. So that's actually the assumptions. So what else we need later on? We need the properties. So let's go with the properties. When we will calculate the properties, we actually need the film temperature. And here, film temperature means TF, it is equal the surface temperature and the atmospheric temperature over 2. We know the surface temperature of the fins from the question is 80 and the air temperature is 30, so it will be 55 degrees centigrade. So if we assume that the pressure is at atmospheric conditions, that means 1 atm, so we can say at 1 atm and 55 degrees centigrade temperature, the properties for air from table A15 from SI unit 5th edition book. So we can write it down. The thermal conductivity is 0.02772 watt per meter Kelvin. Viscosity is 1.847 10 to the power minus 4 meter square per second. Prandtl number is 0.7215, and beta, it is equal 1 over TF. This is the volume expansion coefficient, you already know. So 1 over 328 Kelvin. So 55 and 273, that means 328 Kelvin. We converted it into Kelvin. So here actually what we will do now, we will start with the analysis. So when it is we discussed during the lecture, when it is the fins, rectangular fins, the characteristics length, we can consider it is actually the length of the fins in the vertical directions, as we do not know the spacing. Okay, in some cases we discussed that we can use the other one for the characteristics length, but here the length of the fins, it will in the vertical direction, we will consider this is actually the characteristics length. So I can write it like this: characteristics length, it is equal the we can write length in vertical directions. So length of the fin in vertical direction. So width is 18 centimeter, or we can say the characteristics length, it is equal 0.18 meter. So this is the characteristics length. So from the flowchart, at first we need to calculate the Rayleigh number, right? We need to calculate the Rayleigh number, then we will calculate the spacing. So the Rayleigh number here for this characteristics length, it is equal the gravity, the volume expansion coefficient. You know why we calculated the volume expansion coefficient, beta, L cube, viscosity square, and Prandtl number. So from the table we got this, and we got the Prandtl number, we got this value, and we already know Ts and T infinity. So what we need to do here, let's substitute the value. It is 9.81. Beta is 1 over 328. Surface temperature, you can remember it was 80. It is 40. Characteristics length 0.18 meter cube. Kinematic viscosity 1.847 and 10 to the power minus 5. This is a square, and the Prandtl number is 0.7215. So we will get it is 1.845 and 10 to the power 7. So this is the Rayleigh number we got. So when we have this Rayleigh number, our ultimate target is we actually want to calculate the optimum spacing. Okay, so we will now use that expressions for optimum spacing. So optimum spacing, it will be, so if we write it like this, so the formula for optimum spacing, it is actually, we define SOPT is 2.714, the characteristics length and the Rayleigh number power 0.25. So substitute the value 2.174, characteristics length is this, and Rayleigh number we just got it 10 to the power 7 and the power is 0.25. So we got it is 7.45 millimeter, or you can say 7.45 and 10 to the power minus 3 meter. So this is the spacing, the optimum spacing. It was the first question. The second question is we need to calculate the rate of heat transfer. So that means if we want to calculate the rate of heat transfer, we need the surface area. If we want to get the surface area, we need the number of fins. So let's start with the rate of heat transfer. So the rate of heat transfer, to get this rate of heat transfer, what we will do, we will calculate initially, we will calculate the number of pins. Actually, what we found here, the fin in the optimum spacing is 7.45, and the fin thickness, it was 1 millimeter. So that means it is about 8 times than the thickness of the pins. Therefore, we assumed earlier, you can remember that the spacing is applicable. So yes, because the thickness is relatively small. Anyways, so we need the number of fins now. We calculated the spacing, so we need the number of fins. So N, it is equal to W S over T. W is the width. It is 1.2 meter wide. Okay, and S, actually the spacing we just calculated. So as we are using in meters, so let's use this value in meters. So 0.00745 meter, and the thickness, so 1 millimeter, 0.001 meter. So that means we will get approximately 14 fins here. So if once we know this number of fins, we know the rate of heat transfer Q, it is equal AS delta T. So we need the convection heat transfer coefficient as well. So now let's calculate the heat transfer coefficient. So the heat transfer coefficient, Hayes, we know, this is actually the equation 9.33 we discussed during the lecture. So it is actually the Nusselt number, okay, Nusselt number, the thermal conductivity, and the optimum spacing. So we already know Nusselt number for optimum spacing, so optimum Nusselt number from the formula from the literature I discussed during the lecture. So maybe you already know that the Nusselt number, it is actually constant, 1.307. So we already discussed it, so I'm not going to discuss it again, because what I said, it will increase the length of the video. So we discussed in the lecture. So if you missed the lecture, so then go through the lecture recordings. So it is 1.307 and the thermal conductivity is 0.02772, and the optimum spacing we got it is 0.00745. So as the nozzle number is constant here, we already had the value, and the thermal conductivity, it is constant. So the highest heat transfer coefficient is 4.863. Alright, so now we will calculate the rate of heat transfer. So the rate of heat transfer, it is equal Q equal Hs As delta T, or we can write it as Hs, the number of pins to the area, and Ts minus T infinity. So Hs, we got it is 4.863. This is 2. Number of pins, we got it is 14. The length is in the vertical direction 0.18, and the height, it is 0.024 meter, and the temperature difference is 80 minus 30. So we will get it is 24.9 watt. This is the rate of heat transfer. So we got the rate of heat transfer is this. That means this heat sink, when we use some different shapes of fins, we usually call this as heat sink. So this heat sink will or can dissipate this amount of heat by natural convections. Okay, and the rate is like 29.4. So that's actually the solutions of this problem, and you will see what we did. Initially we calculated Rayleigh number, optimum spacing, and then we calculated the heat transfer coefficient. Then we got the rate of heat transfer. So